We physicists have waited 100 years, beginning around 1916, for this photograph. It is a nearby black hole, perhaps one of the most captivating and puzzling phenomena known to mankind. They are immense in power yet, at the same time, almost imperceptible to us. A black hole weighing perhaps 2 to multiple times the mass of the Sun is an extraordinary force. However, thanks to research conducted over the last 2 or 3 decades, we've gone from knowing almost nothing about them to understanding more and more. And now, things have just gotten even more astonishing. Michio Kaku recently revealed that we have finally caught a glimpse of what's inside a black hole. This new information sheds light on details that the scientific community may have overlooked from the very beginning. Join us as we dive deeper into black holes and uncover what lies inside. What are black holes? Before we explore the details of what Michio Kaku discovered, we need to examine the basics. Although most of us have some idea of what black holes are, there are still gaps in our knowledge. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept was entirely theoretical. It took an additional 50 years for the scientific community to find evidence that black holes actually exist. This breakthrough occurred in the 1960s when scientists studying the Cygnus X-1 celestial body observed an unusually bright blue star emitting X-rays. This star was not a simple celestial object. It appeared to be orbiting an enormous, invisible mass. Upon further examination, scientists realized the X-rays weren't just moving around. They were being sucked into this massive, unseen force. Thus, the term black hole was born. This discovery was monumental because it provided the first evidence that black holes were real and not just a product of Einstein's imagination. While this was an astonishing revelation, it also meant that an incredibly powerful and mysterious entity existed in space, one we desperately needed to learn more about. Cygnus X-1, the first known black hole. Following the discovery of Cygnus X-1, scientists worldwide began searching for other black holes. They found that there might be nearly 100 million black holes in the Milky Way alone. However, because black holes are incredibly difficult to detect, we still don't have an exact count. What is clear is that there are millions of black holes in our own galaxy, making them even more crucial to study. The primary concern with black holes is always their gravitational pull. Their gravitational force is so extreme that anything entering them is compressed beyond recognition into a singularity. In simpler terms, black holes are like gigantic vacuum cleaners, pulling everything in. One of the most terrifying aspects of black holes is the spaghettification process. If someone were to fall into a black hole, they would be stretched thin like a noodle before ultimately disintegrating. This means that no one should ever attempt to approach one. Yet, black holes are everywhere. Are we in danger? The closest known black hole to Earth is about 500 light-years away. While that might seem far, it's still close enough to raise concerns. In 2021, researchers successfully captured the first clear photograph of a black hole, the M87 black hole. This image was taken over several nights, and with each photo, scientists gathered more and more data about this cosmic phenomenon. By piecing the individual images together, scientists discovered that black holes are composed of 3 distinct layers, rather than being just a gaping void, as many people assume. 1. The event horizon. This is the outermost layer. Once you pass the event horizon, there is no turning back. You will be inevitably drawn into the black hole. 2. The photon sphere. In this region, light itself is trapped, circling the black hole due to its immense gravitational pull. 3. The singularity. This is the very core of the black hole, where all matter is infinitely compressed. At this point, the known laws of physics break down, and we have no way of predicting what happens next. Studying black holes, the challenges. Each black hole is unique. While they all follow the 3-layer structure, their specific behaviors can vary greatly. If this were any other celestial object, we could simply use telescopes to study it in detail. But black holes present a unique challenge. Because nothing, not even light, can escape a black hole, scientists must study them indirectly. They do this by observing the radiation they emit and the way gas and dust interact around them. Sending a probe into a black hole is impossible, as anything that crosses the event horizon is pulled toward the singularity and compressed into an infinitely small point. Given these limitations, investing billions of dollars to peek inside a black hole is not feasible. Instead, scientists continue to develop innovative techniques to study these mysterious cosmic giants from a safe distance. Since the second the test draws near sufficiently, it will basically be raced into nothingness. As a result of that reasonable issue, specialists are left with no decision except to concentrate on these objects in a two-layered manner, despite the fact that they are three-layered singularities. To make matters considerably more challenging, there are also the two issues of every dim opening being unique and the laws of physics, as we probably are aware, breaking down when we attempt to examine the inside of dim openings. Conventional methods of scientific inquiry don't actually apply to the investigation of dull openings. That doesn't mean specialists haven't been occupied. There are loads of various theories and explanations for dim openings, and with each one, things get increasingly fascinating. Perhaps the most compelling theory about the formation of dim openings is that they are produced from collapsed stars. By then, when a star depletes its fuel, it can no longer generate sufficient energy to counterbalance the force of gravity that is constantly pulling inward. So, the star begins to collapse on itself, contracting and becoming denser as it does. If the star is large enough, this process can continue until it transforms into a singularity. To comprehend the nature of dim openings in depth, NASA scientists directed their focus toward the center of the universe, M87. Cosmologists observed a truly powerful whirlpool of extremely hot hydrogen gas that was rotating at a stunning speed of 1.2 million miles per hour. The sheer force of the rotating gas disk should have made it violently fly apart in all directions. However, it didn't. Researchers found that there must be a titanic mass gathered at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns, and it had to be a dim opening. But that's not the only theory regarding dim openings. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a rotating dim opening. He showed that rotating dim openings wouldn't collapse into a point, as previously thought, but rather into a ring of fire or a thin disk. The disk would rotate so rapidly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the ergosphere, and it's the region surrounding the dim opening where the laws of physics begin to break down. However, the most intriguing aspect of Kerr's solution was that it predicted the presence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical tunnel through spacetime that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a dim opening, rather than being crushed into oblivion, they would be sucked down a tunnel through the ring of fire and ejected out of a white opening into a parallel universe. To understand how this works, we need to look at the concept of spacetime in Einstein's theory. The reality we experience isn't made up of separate elements but is interconnected, forming a four-dimensional fabric known as spacetime. Objects with mass warp this fabric, creating a gravitational field that pulls other objects toward them. Now, imagine a piece of paper representing spacetime. If you put 2 points on the paper and draw a line between them, this represents how objects travel through spacetime. But what if you could fold the paper in half and create a shortcut between those 2 points? This is the concept behind wormholes. The idea is that dim openings might be gateways to another universe, just like wormholes. Dim openings hold both immense power and profound mysteries, making them endlessly fascinating subjects of study. Their gravitational pull can consume entire stars, and at the same time, they are also thought to be windows into parallel universes. The more we learn about dim openings, the more we uncover about the fabric of spacetime and the fundamental laws of nature. While we may not have all the answers right now, one thing is certain. Dim openings are likely to remain one of the most profound and puzzling phenomena in the universe for a long time to come. As we delve deeper into the mystery of dark openings, new discoveries and theories continue to challenge our understanding of the universe. One of the most fascinating aspects of dark openings is how they warp space and time. According to Einstein's general theory of relativity, mass and energy distort the fabric of spacetime, and this effect becomes more extreme near a dark opening. Close to a dark opening, the warping of spacetime is so intense that it can lead to bizarre and seemingly impossible phenomena. For example, the closer you get to a dark opening, the more time itself starts to behave strangely. This is due to the warping of spacetime, a phenomenon known as time dilation. In practical terms, this means that if you were orbiting a dark opening, time would pass much more slowly for you compared to someone far away. If you were to fall into a dark opening, an observer watching from a distance would see you slow down and eventually freeze at the event horizon, never quite crossing it. However, from your own perspective, time would proceed normally, and you would continue falling toward the singularity, where the laws of physics, as we know them, break down. This brings us to the most mind-blowing question: what happens inside a dark opening? While it's impossible to send probes or astronauts into a dark opening to answer this question directly, physicists have proposed several theories. One possibility is that the singularity at the center of a dark opening could be where the fabric of spacetime itself tears apart, and the usual rules of physics no longer apply. The extreme gravitational forces would cause any object to be crushed to an infinitely small point, with its mass compressed into a singularity. What happens beyond this point is a mystery, as our current physics theories cannot explain the behavior of matter and energy in such an extreme environment. One interesting idea comes from quantum mechanics, the branch of physics that governs the behavior of tiny particles. Quantum mechanics suggests that spacetime might not be a smooth, continuous fabric but rather could be quantized at the smallest scales, meaning it could be made up of discrete building blocks. This idea, known as quantum gravity, could provide a new framework for understanding dark openings and the singularity at their centers. Some researchers even speculate that this framework could explain why dark openings don't violate the laws of physics. Perhaps they don't truly contain a singularity after all. Another intriguing concept is the information paradox associated with dark openings. In quantum mechanics, information about a particle's state must be preserved. But when matter falls into a dark opening, it seems that the information about that matter is lost, violating a key principle of quantum theory. This paradox has sparked much debate in the scientific community. Some researchers propose that the information is somehow encoded on the event horizon, in what's known as the holographic principle. This would mean that everything falling into a dark opening isn't lost but is instead stored on its surface and could eventually be released in some form. As we continue exploring the mysteries of dark openings, a key discovery is the existence of supermassive dark openings at the centers of most galaxies, including our own. These dark openings can be billions of times the mass of the Sun and exert a profound influence on the behavior of their host galaxies. Recent observations of dark openings, such as those in the centers of galaxies, like the famous M87 dark opening, have provided new insights into how these cosmic giants shape their surroundings. The M87 dark opening, for example, was imaged in 2019 by the Event Horizon Telescope (EHT) collaboration, marking a major milestone in dark opening research.